Welcome to the Explainer. So if you've ever dealt with a stuttering frame rate in a high-end game, a terribly laggy architectural render, or, motion sickness in VR, then you already know the absolute pain of hardware limitations. Today, we're diving straight into some fascinating source material that unpacks the massive computational burden of modern graphics rendering. Specifically, we're zeroing in on the infamous memory bottleneck, and we're going to explore active memory expansion and the future rendering technologies that are quite literally changing the game. Here's our roadmap for today. We're going to cover Section 1, the rendering memory bottleneck, followed by Section 2, industries demanding faster rendering. In Section 3, we'll answer, what is active memory expansion? Then we'll look at hardware-software co-design, Unity's virtual texturing cache, and finally, wrap up with energy-efficient rendering futures. Let's get right into it. Section 1, the rendering memory bottleneck. Okay, let's dive into this. Even the absolute most powerful modern hardware on the market today is plagued by this core limitation. So we really have to ask the fundamental question here. Why do modern graphics still bottleneck? Well, think of your computer's processing power as this massive, multi-lane data highway, right? Your CPU and GPU, they can crunch numbers at blistering speeds. But when it actually comes time to move that graphical data from storage into memory, that superhighway suddenly funnels into a narrow dirt road. This limitation in memory bandwidth is exactly what causes a massive traffic jam of data in your rendering pipeline. So, what exactly is causing this massive pileup in your graphics memory, or VRAM? First up, we've got high-resolution textures. 4K and 8K displays require textures that can consume several gigabytes of memory per scene. Then you add in the sheer geometric complexity and massive polygon counts of modern 3D models. Throw in the frame buffer memory allocation needed for advanced techniques, and the insanely huge data structures required just to calculate real-time ray tracing, and you can clearly see why our hardware gets completely overwhelmed. But interestingly, the problem isn't just about total storage capacity. It's actually about how the data is accessed. And this brings us to cache coherency issues. When rendering operations access memory in these inefficient, irregular patterns, it results in cache misses and memory stalls. So your incredibly fast processor ends up literally just sitting there, twiddling its thumbs, waiting for data to arrive from memory. It completely disrupts the efficiency of the entire rendering pipeline. Section 2, industries demanding faster rendering. Now, solving this memory bottleneck, it isn't just a fun puzzle for computer scientists. It's absolutely critical across the entire tech sector. The market pressure right now is immense, and it's being driven by highly diverse industries pushing the very boundaries of real-time graphics and visualization modeling. We're talking about gaming and entertainment, obviously, but also architecture, engineering, and construction, which heavily rely on real-time visualization for collaborative design. Then there's the automotive industry, powering autonomous systems and those high-fidelity dashboard displays. Add in cloud services and mobile content creation, and you're looking at a global economy that is desperate for rendering acceleration. The stakes here are very real. As the source material points out, virtual and augmented reality applications require ultra-low latency rendering just to prevent motion sickness. Think about that for a second. We aren't just talking about an abstract technical limitation here. If memory bottlenecks cause frame drops in a VR headset, it literally causes visceral human discomfort. The stakes for getting this right are highly relatable and honestly incredibly high. Section 3. What is active memory expansion? So how do we actually fix it? Well, active memory expansion is an approach that dynamically expands available memory resources during rendering operations via intelligent allocation. It creates this beautifully fluid and responsive memory ecosystem. Instead of a rigid system where memory just runs out and everything crashes or stutters, this system intelligently adapts to the workload in real time. It's constantly anticipating exactly what the renderer is going to need next. To really grasp this, let's contrast the old, rigid, static memory configurations with the new dynamic resource allocation. Static configurations are exactly that, rigid. You have a set amount of memory, and if a high-res texture exceeds it, bam, you hit a bottleneck. Dynamic allocation, on the other hand, uses advanced predictive algorithms to proactively allocate and expand available resources based on scene complexity and performance targets. It proactively stops bottlenecks before they even happen. It's a total game changer. Section 4, Hardware-Software Co-Design. But how is this practically engineered behind the scenes? Historically, we had these totally isolated hardware and software boundaries. Hardware engineers built the chips, software engineers wrote the code, and everybody basically just crossed their fingers and hoped it all worked well together. But active memory expansion completely relies on synergistic co-design. We're now seeing custom memory controllers and specialized cache hierarchies built to work in perfect synchronization with software algorithms. The software scheduler predicts what data is needed, and the specialized hardware cache is explicitly designed to receive and process it efficiently. Let's ground this theory in reality for a second by looking at some cutting-edge core patents in memory expansion. One patent details a multi-level brick cache system that actually optimizes the memory hierarchy based on past and current rendering parameters. Another really fascinating patent involves the GPU writing geometry rendering results directly to on-chip memory instead of sending it all the way out to main memory. By keeping that data on-chip during illumination rendering, you drastically save bandwidth and eliminate a massive chunk of that data traffic jam we talked about earlier. Section 5. Unity's Virtual Texturing Cache. Shifting from the macro to a more micro-level example of how developers fight these bottlenecks today, the Unity manual details a brilliant practical application called Streaming Virtual Texturing, or SVT, cache management. This is just a perfect illustration of active cache management, successfully bridging the disk, the CPU, and the GPU to handle massive textures without grinding the whole system to a halt. Let's walk through how this builds a highly efficient pipeline. Step 1. SVT reads multiple texture tiles from the incredibly slow disk into a combined tile page. Step 2. The CPU cache in main memory retains this page. Why? Because the system predicts that if you need one tile, you're highly likely to need the neighboring tiles in the upcoming frames. This completely prevents further slow disk reads. Finally, step 3. The system feeds this data into fixed-size GPU caches for final graphics formatting. It's a beautifully choreographed dance that entirely bypasses that slow dirt road of disk reading. Section 6. Energy-efficient rendering futures. Now, we've talked extensively about speed and performance, but there is a globally impactful benefit here too: power efficiency. The absolutely crucial point is this figure right here, 30 to 50%. That is how much energy consumption can be reduced. How? Through something called proximity computing. You see, in traditional setups, moving massive amounts of graphical data back and forth across a system consumes a ton of power. By performing computations closer to where the data is actually stored, like those on-chip rendering patterns we discussed, we drastically reduce the physical distance the data travels, saving up to half the energy. For mobile devices and massive cloud data centers, this is completely revolutionary. And this points us directly toward the future. Emerging hardware technologies like resistive RAM and phase change memory offer inherently lower power consumption profiles than our traditional DRAM. When you start combining these new materials with advanced machine learning-based predictive caching, our power management and energy efficiency gains are just going to skyrocket even further. Which brings us to our final thought for this explainer. With memory bottlenecks disappearing, energy consumption dropping, and predictive algorithms providing near-instant access to massive pools of data, is the future of digital worlds limited only by our imagination? As we eliminate the technical friction of rendering, the only constraint left on the worlds we can build, visualize, and explore is going to be human creativity itself. Thank you so much for joining me. I really hope you found this deep dive into active memory expansion as fascinating as I did. Keep learning, and I'll catch you next time.